Okay, this is part 2 of the example problems on the definite integral section of the textbook. As I mentioned at the start of part 1, just a reminder that these example problems are about the definite integral. However, we have not gotten to the fundamental theorem of calculus yet. That's the next section. So we do not know how to evaluate definite integrals by taking the antiderivative. That's the main method that once you're done with calculus, that's how you evaluate definite integrals. You use the antiderivative. That's quick and easy. At this point in section 5.2, we learned what the definition of the definite integral is as far as like an infinite sum. It's the limit as n approaches infinity of a Riemann sum that's been set up over an interval on a function. So that's all we know about the definite integral. So all of these example problems are being looked at from that lens. Now, at the end of section 5.2, we did talk about certain properties of definite integrals. And so we're going to use those properties as well. In particular, in this video, we're going to use those properties. And these properties, though, just to point out, apply even once we learn the fundamental theorem of calculus and we use the antiderivative method. These properties apply then as well, because it's not like once we learn the fundamental theorem of calculus, the definite integral changes. The definite integral is the definite integral. Okay, so for example, we learned what is this here? Well, you might look and say, well, is this the equation for a circle? It doesn't. This is x to the fourth. I mean, we have no way to evaluate this. That's true. At this point, we don't, if the limits of integration were different. But both of the limits of integration are the same. In that case, we know that this is equal to 0. They could have put any function here. It wouldn't matter. If the limits of integration are the same, this is equal to 0. That's a property of a definite integral. It doesn't matter. Once we get past the fundamental theorem of calculus, it's still this is a property of just definite integrals in general. Again, it's not like the definition of the definite integral is going to change once we learn the fundamental theorem. So all the properties that we're going to be using in these example problems in this video, these are properties of definite integrals. Okay, if the definite integral from 2 to 8 of f of x dx is equal to 7.3, and the definite integral from 2 to 4 of f of x dx is equal to 5.9, then find the definite integral from 4 to 8 of f of x dx. And so the property that they're wanting us to use here is this property, that if you going from a to b of f of x dx, and then you add that to an integral going from b to c of f of x dx, then that's equal to the integral from a to c of f of x dx. And this makes sense because when you think about this in the context of areas under a curve, like if this is f of x, and then so here's a, here's b, and here's c, then what we're saying is this area plus this area is equal to the entire area from a to c. And now the only confusing part is, well, okay, yeah, if you've got a function that's always positive like this, and all of the a, b, and c are positive, then that's okay. But what about the whole net area idea, right? What if you've got a's or b's or c's that are negative, and you're crisscrossing above and below the x-axis? Then what's the case then? This applies in general for all scenarios. This is like universal. So all we have to do is say so if we write this out here, this goes from 8 to 2, this goes from 4 to 2, this goes from 8 to 4. So we've got the integral from 2 to 4 plus, and then the integral from 4 to 8 is going to be equal to the interval from 2 to 8. Okay, now we know this integral. They give us this. And then we know this integral. They give us this. but we don't know this. And so we can see, we can solve for this is equal to 7.3 minus 5.9. So 1.4. That's it. This integral is equal to 1.4. Okay, if the definite integral from 0 to 9 of f of x dx is equal to 37, and the definite integral from 0 to 9 of g of x dx is 16, then find this definite integral. Okay, so we know that we can separate this into two separate definite integrals. So we have 0 to 9 to f of x dx plus 0 to 9 3g of x dx. Okay, now we know we can take these constants and out to the front of the integral. So this is okay, and then okay, now they give us these from 0 to 9. F of x dx is 37. So this is 2 times 37, and then this is 16. So this is 3 times 16. 2 times 37 is 74. 16 times 3 is 48. 74 plus 48 is 122. All right, find the definite integral from 0 to 5 of f of x dx if this is f of x. It's this piecewise function here. Okay, so what can we, is this integrable? Is this f of x integrable over the discontinuity? Yeah, you can do a definite integral over a discontinuity because it's just the area under the curve. So we can think about this. We're going from, so 1, 2, 3, 4, 5. Okay. All right, so we're going from 0 to 5. When x is less than 3, the function is equal to 3. Okay, so, and then open circle here, because it's not defined when x is equal to 3. Okay, and then the function is equal to x when x is greater than or equal to 3. And so you draw a piecewise function, you just draw the function x like normal, but then you erase where it's not, it's outside of the domain. So what we would do is, like, this is x, the line x goes through the point 1, 1. So we do this. It would go, well, okay, we can come here, and so the line actually passes through this point as well. So this point is defined. And let me do it this way. Okay, like that. And then you just erase where it's outside of the domain. So this function actually is continuous. Okay, so that's the function. And I mean, actually it goes off, it goes off to infinity, but we're just looking at, so 1, 2, 3, 4, 5, we're looking at this, the interval from 0 to 3, 0 to 5. So we're looking for this area under this area here. And so what they're trying to show is that we can do this manually, right? We can find this area manually using regular geometry. And so what is the area of this rectangle? That's 5 times 3, so this is 15. So we're going to have, this is going to be the integral from 5, or 0 to 5 of f of x dx is equal to 15 plus, and then 1/2, and then the base is, we've got 1, 2, base times height is what? The height should be 2. Because this is y is equal to x. Yeah. So this is 15 plus 2. 17. Okay, use the properties of integrals to verify the inequality without evaluating the integrals. All right, let's take a look at these comparison properties that were discussed in section 5.2. See if this can help us. So we're trying to verify that this integral is going to be greater than or equal to 0. Well, okay, the first thing we can look at is we can make sure that the limits of integration are in like ascending order. So we go from 0 to 4. So that's, we have to, if this was going from like 4 to 0, then everything would be kind of switched. But this is going from 0 to 4, so everything's normal there. Like, in other words, if we had an area like this, exact, like the function is positive, you're getting the definite integral. Here's A and here's B. It's a positive area, right? But if the limits of integration are going from the lower limit they put as B and the upper as A, then it's going to be negative. So everything like flips. But that's not the case here. So okay, so one thing we know we can do is we can separate this out. And so we can bring the minus sign out front like that. Okay. Well, okay, I'm not sure if this is going to help. Let's try this. So we know that this is a parabola. X squared minus 4x plus 4 as a whole is a parabola. And so what kind of parabola is this? All right, so we complete the square. Well, actually, we could factor this. So, yeah, this is x minus 2 minus 2. So, yeah, this is x minus 2 squared. But even if this wasn't factorable, we could still complete the square to put this in vertex form and see what the parabola is in space and get an idea of if the function is if that parabola is in the positive region from 0 to 4. Here we see what we have is this is in vertex form. This is f of x is equal to, so x minus 2 squared, and then it's shifted up or down by 0. So this is the parabola, x squared, which is like this, but just shifted to the right 2 units. And so if we're integrating from 0 to 4, which is like, it's going to be positive. The area is going to be positive. This is going to be greater than or equal to 0, for sure. Right? This is the parabola, x squared, which is always positive, shifted to the right 2 units, but it's not shifted up or down, so it's positive no matter what. So it doesn't matter what interval you choose, this definite integral is always going to be greater than or equal to 0. Okay, so let's bring back the comparison properties. So that I'm assuming they want us to look at this kind of sandwich property here between a smaller m and a larger m. This is a smaller m, this is a larger m. And so what we can do is, just to get a sense for what this function looks like, let's graph this. So, okay, all right, one. So this is, 3, negative 3, 2, minus 2. Okay. So we're going from, well, let's do this to make it easier to see. This will be minus 1, this will be 1, this will be 1, this will be minus 1, and then we'll Go up a little bit more. Now we have a better visual. Okay, so when x is equal to 0, the function is equal to 1. When x is equal to minus 1, the function is equal to root 2. So root 2 is 1.41. So this is 1.5. Here's 1.25, so, kind of right in there. When x is equal to 1, the function is equal to root 2. Okay, when x is equal to 1/2, you've got 1.25. So the square root of 1.25 is 1.12. There's 1.25, so about like that. And this is an even function. It's symmetric about the y-axis. Okay, so in this interval, it's doing, I don't know if that's the best points here, but, it's something like, that's probably, I can just admit that I didn't draw those points the best. It's something like that. Okay. So what we can see there is that if we come back to this property, the idea is these values, this lowercase m and this uppercase m, so like, okay, the lowercase m is less than or equal to all of f of x over the interval. And the uppercase m is greater than or equal to all of fx over the entire interval. So our lowercase m, we could say anything. We could say this is lowercase m or this is lowercase m, but let's make the absolute minimum over the interval be lowercase m. So lowercase m we'll say is 1. And then uppercase m we'll say is, this was root 2. Okay? And so a property of definite integrals is that if we find a lowercase m and an uppercase m that satisfies this condition, and this does, this lowercase m and uppercase m satisfies this condition over the interval, right? It's this condition over the interval from x is equal to a to b. So if that's the case, then this is true. So we don't know if this is true, but we can make a similar inequality and then compare that to this. So what do we do here? We multiply lowercase m by b minus a and uppercase m by b minus a on this side. So what is b minus a? That's 1 minus 1, that's 2. So 1 times lowercase m, and then we put the integral, and then 2 times uppercase m. And there you go, there it is. All right, use property 8 to estimate the value of the integral. And there's property 8. Okay, that's the same property we just used. So what they're saying is just set up this inequality, and we're going to know that the value of the integral is going to be somewhere between these two values. So how do we set up the inequality? Well, let's draw the function over the interval from 1 to 0. So it's going to be positive in that interval. So 0.5, 1, 1.5, 2, 1, and this is 1. When x is equal to 0, the function is equal to 0. When x is equal to 1/2, the function is equal to 1/8, which is 0.125. So this is 0.5, this is 0.25, something like that. And when x is equal to 1, the function is equal to 1. Okay, so it's like that. Okay, so property 8, we need to find capital M and lowercase m. And so we could use this as capital M, but then that wouldn't be the best estimate, right? We're trying to use the smallest capital M as possible and the largest lowercase m as possible. So we'll do capital M is going to be 1. We know that over this interval, the function is less than or equal to 1. All values of the function within this interval are less than or equal to 1. And then over this interval, all values of the function are greater than or equal to 0. And so what the property says, property 8, is that we can the actual integral, the definite integral, is going to be sandwiched between lowercase m times the b minus a and uppercase m times b minus a. So what is b minus a? It's 1 minus 0. So, okay, 1 times 0 is 0. One times 1 is 1. This is somewhere between 0 and 1, this integral. Okay, same problem. All right, so let's, just to get an idea of this, so x times e to the minus x. Store that as e. Okay, so e with x is equal to 0 is 0. E with x is equal to 2. And this is, okay, e with x is equal to 1. All right. So, I mean, I guess that they want us to use the closed interval method to get the absolute max and min, to get lowercase m and uppercase m. So we've got the function f of x is equal to x e to the minus x over the closed interval from 0 to 2. So f of 0 is equal to 0, and f of 2 is equal to 2e to the minus 2, which is about 0.271. Okay, so now that's the endpoint. So now we need to evaluate we need to get the critical points. So there's the derivative. So now let's solve for when this is equal to 0 for x. X is equal to 1. And is there anywhere where this doesn't exist? No. This exists for all numbers. So x is equal to 1 is a critical number. So we want to now evaluate the function at x is equal to 1, and that's 0.368. And so now we just compare these three numbers, and whatever's the largest is the absolute max, whatever's the smallest is the absolute min. So we can see that capital M is going to be 0.368, lowercase m is going to be 0. And so with that, and then, okay, what's b minus a? That's 2. All right, so now we can use property 2. 2 times 0 is 0. X e to the minus x dx. And then 2 times 0.368. So it was this times 2, which is, yeah. Well, hold on. No, that's not right. Okay. It's 2, this times 2, 0.74. And wait, well, let me, and just to see, we might want to do this exactly. So this was f of 1. Okay, so let's, and then that times 2, yeah, so 2e to the minus 1. That's the exact answer. There we go. So this integral is somewhere in between 0 and 2e to the minus 1.